Why, hello there, children. So today we're going to continue to look at the slope of a curve, and we're going to be using our limit definition like we did last time. Let's start with a question that's just like last time. I'll put up a random polynomial, and you find the derivative. So now I would pause the video. You, using perfect notation, find the derivative using the limit definition, and then check my work. All right, so there is our derivative, right? And again, let's remember what the derivative is. This equation is the slope at any point on this original curve here. All right, so today we're going to do three more interesting derivatives. And I said find f prime of x using the limit definition. So we want to find the derivative, the slope, the equation for slope at any point on this original function using the limit definition. And just because it looks a little different, you're going to do it exactly the same. So let's maybe first just write the limit definition out. So just because this is a polynomial, nothing changes. So go ahead and plug in that function. And again, notation is going to be really important, so make sure, I almost forgot the limit in my limit definition. Don't forget that. Always go back and check. So what you did, again, is plug in x plus delta x instead of x, right? For every x you see, it should become an x plus delta x. So that's our first point. Minus y1, the original function, right, all over delta x. And I look at this and I think, well, I can't really cancel anything nicely like the polynomials did automatically. Well, it says subtraction, so let's subtract. We don't have the same denominator, so we go back to Algebra 2 and Algebra 1, and we need to make these like denominators. So see if you can first subtract these, and see if you get the same answer that I get. Right, when we subtract these, please make sure you distribute this negative to both of the pieces. And very similar to what happened when we were doing polynomials, these two x's cancel. Rewrite what happens after they cancel. Right, I don't want two divisions here, divide, divide. So instead, when I rewrite this, let's not divide by delta x. Let's multiply by 1 over the reciprocal. And the nice thing is, if I multiply by the reciprocal, when I multiply by the reciprocal, well, those delta x's cancel, and I can rewrite, and then nothing stops me from actually taking the limit. So again, this is our derivative of our original function, the equation for slope at any point on this original curve. All right, so very similar question. You try this one. You're going to set it up the exact same way as before, but we have this additional +2 there. So pause the video and see if you can do the whole question out and see if you get what I get. So sorry, the power in my projector randomly just went out. So if we cancel these things, we get, there's going to be a little sloppier because I'm doing it by hand. We get the limit of just the negative delta x's left. And we have our denominator. And we have divide by delta x, but let's not have excuse me, let's not have another division. Let's actually multiply by 1 over delta x, by the reciprocal. And in this case, again, what happens is our delta x's cancel. And so I get the limit as delta x approaches 0 of -1 Oh, my power of my board just went back on. Right, and so here, now I can take the limit, I plug in my 0, and I get -1 over the quantity x plus 2 quantity squared. Again, that's the slope at any point on this original curve. So let's do one last question before you begin your classwork. Our last question has a radical, so just first of all plug that into your limit definition. So I look at that, and y2 is x plus delta x, the square root of it, minus square root of x, which is y1, over delta x. And I look at this, and I should think back to my last class and our limits questions. Anytime I saw the radicals, well, multiplying by a conjugate usually helped. Try that. Pause the video, multiply by a conjugate, and see if you could finish the question up. All right, and there we have our derivative again. Again, that's an equation for the slope at any point on this original curve. You might be asking yourself, shouldn't I rationalize? We're going to stop rationalizing now that we're getting into the beginning of calculus because it's going to make things easier if we had to take the derivative again. We could take the derivative of this guy and we'd get the second derivative, but we'll leave that for a different time. So what we're going to do today, what you're going to do today, is see if you can come up with a pattern. When you were looking at those polynomials, some people started to say, this kind of looks familiar. Something perhaps is going on here that might always happen. So you're going to do at least one of each grouping, either 1 or 2, or 3 or 4, or 5 or 6. Actually, maybe do 5 instead because it's the only one with a third power. And then do or 7 or 8. And hopefully afterwards, if you fill those out and you start to look at the pattern, maybe you could come up with a pattern for any polynomial where I have x raised to some integer power. Well, what would the derivative be? Or if I had c is just some constant. If I had some constant times x raised to some integer power, well, what's going to be the derivative for any polynomial like that? So that's your goal today. I will tell you the secret tomorrow. And after you come up with hopefully a pattern, for homework, try these 2 questions. And I'll also post the worked out solutions to these so that you can begin, so that you can check your work. And please be really careful with notation. I'm careful with notation. I want you to be careful with notation as well. All right, thank you.